I'm sorry, I'm swearing.
Yes, ma'am. It didn't make a whole lot of sense. I asked if anyone had any questions, and you didn't ask any questions. You just made a statement. That didn't help.
The entire thing, like, it made sense while you were talking about it during class, and then I sat down to do it.
What, did you get them right or wrong?
Wrong.
Oh, dear.
Because I just, like, put arrows over all
That's not the idea. Maybe you can come in before or after school and get some extra help. Okay. Or check out my awesome web help video where I explain everything.
Really, I don't understand anything.
Yes, sir.
On the video, are we allowed to get student voices?
Yeah, we can have student voices. We just can't show the images.
He's funny.
Hey, I'm going to ask you to put that pink piece of paper where I don't know who it belongs to, but will you make it go bye-bye? Like really bye-bye, not just sitting. That's not really bye-bye. That's like hello again in a minute when Mr. Sampson turns to say, can you just make it go bye-bye? Like someplace far away.
Burn it.
I don't want you to burn it. Okay, great. Okay, so I'm super excited for you today because today is the day where you really begin to get a sense of the wonderful power of the periodic table that the average viewer of said table doesn't comprehend. Oh, there it is. I thought it was stolen. Okay. All right, so the thing is today is I want you to consider this about atoms. Atoms are like onions and ogres.
They have layers.
They have layers.
Like
You're
cake.
right. Like cake or parfaits, which I hear are the most delicious thing ever, but I've never eaten one, so I wouldn't know.
They're not that.
Is there anyone here who doesn't know what I'm talking about? You've never seen Shrek?
Oh, yeah, I've seen Shrek.
Okay.
I thought you were talking
I have
about-
people over the day who... Is there anyone here who's never seen Shrek? Anybody?
Good.
Oh, darn. Because it's fun to think, like, if you've never seen Shrek. Is there anyone here who's never seen Groundhog's Day?
You guys.
I'm not saying a word. Don't say a word. Don't say a word. You have to see this movie. I love watching Groundhog's Day with somebody who's never seen Groundhog's Day. It's just the best. You just get to a point in the movie and they're like, what? It's so great. All right, anyway. All right, so I'm glad you've seen Shrek so you understand about layers, Dawson. Okay, so let's think about this. How many layers does a hydrogen atom have? Uno. All right, here it is. It just needs one. The layers are called energy levels, and hydrogen has one of them. How about the element lithium? Element 3. How many layers does it have?
Thrice.
How many?
2.
2. It has 1, 2 layers. And where are you getting this information from anyway?
Periodic table.
Where on the periodic table does it tell you?
On
You
the-
pointed, Kaden. What did you point at?
Little numbers on their side.
Like these ones here?
Just.
These numbers here tell you how many layers, which we call energy levels, an atom has. And it turns out that this is going to have a lot to tell us about the behavior of atoms. So let's just try going. I'm going to go 2 more, and then I'm going to get bored, okay? Let's go to sodium, element 11. Here's the nucleus. Has how many layers?
Thrice.
Eins, zwei, trace.
Veer.
Does anyone know the Keller family?
Yeah.
They're so awesome. They speak English, German, and Spanish, and they don't notice when they're going in between them. It's so weird. You're just like yeah. All right. And potassium, element 19,
Me.
has how many layers?
4.
Ichi. Is it itchy or itch?
Ichi.
Ichi, dos, zwei, and quattro.
Oh, you forgot French.
Where's the French?
Oh,
French is
I meant to say
overrated.
trois. Un, deux, trois. I don't know what. Is it cat?
Quatre.
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 Did I say it right? Quatre. I can't do French. Alright. Hey, looky here. As you go down the periodic table, you're adding layers to the atom, and guess what happens to them? They get big and fat as you go down the periodic table. So where do you think you're going to find the biggest, fattest atoms of all? Down here at the bottom, because they got 7 energy levels in them. And where are you going to find the smallest little adorable, petite, impish-like atoms? Up here at the top, because they only have 1 energy level. That's super easy to do. So let's play this game. Which atom is bigger? Okay, you ready to play which atom is bigger?
Yup.
Which atom is bigger? Copper or gold? Element 29 or element 79? Let's see who's going to play this game for me. Ooh, it's going to be Cameron Larson. How about it? Gold or copper, who's bigger?
Gold.
Hey, you're right. How did you know?
Because it's.
You got to talk like Shrek.
I don't know how to talk like.
I don't either. It has
Michael
more
Myers.
layers.
More layers.
All right. Which is a smaller atom? Okay. A smaller atom, aluminum or thallium, 13 or 81. All right, 13. Why do they keep rolling on 8? It always lands on 8. It landed on 8. Okay. It always lands on 8. Sarah?
Aluminum.
Is smaller?
Yeah.
Yeah. Okay. It's only got how many layers?
3.
This is not a hard concept, is it? Okay. Not hard at all. But wait, there's more. Let's pick someone who's up for a real challenge. Bryce. You look like a man who's up for a challenge. Don't feel bad if you get this next one wrong. Everybody get this one wrong, okay? Which one is bigger, Bryce? Here are your choices. Your choices are. It's not a trick question. There is an actual answer. It's just hard. It's not trick. There's potassium or krypton. Your choices and answers are potassium, krypton, neither. Those are your 3 choices.
Wait, so what's the original question?
Which one is bigger?
What number is KR?
KR is 36. K is 19.
You're saying neither.
Aha.
Wait. Wouldn't it be potassium because its nucleus is bigger?
Potassium's nucleus is bigger than krypton?
I mean, no.
Neither. Going with neither.
No, I'm curious. You have no idea how great you're doing. It's just I want to hear a little bit more of your thinking here.
I don't know. Isn't it though?
It does have something to do with nucleus. I know this. Bryce is wrong. Bryce said what everybody says. What would you expect? I set you up for this, right? Because I said, look, as you go down, you get more layers. 4 layers, 4 layers. Gosh, they should be the same size, but it turns out they're not. Because look here. But you were getting towards there, Kellen, because potassium has 19 protons in its nucleus. It's going to attract 19 electrons, but those 19 electrons are going to arrange themselves in 1, 2, 3. I'm doing great circles. And 4.
Oh, it's an oval.
That! An oblate spheroid. Okay? There's potassium. Now, krypton is going to have 36 protons, which is going to attract 36 electrons, but they're all going to fit at the same 4 energy levels, so it makes sense to think, well, you got 1, 2, 3, 4. Hey, they're the same. Did I make them the same size? See, you'd think the same size, right? Admit it. Didn't most of you think that? But imagine this. Okay. Imagine that these were planets orbiting the sun. This would be Mercury, Venus, Earth, and Mars. Mercury, Venus, Earth, and Mars. All right. I had another awesome idea last period. There's a game you kids, some of you play, Grand Theft Auto. I've heard about it. I've never seen it, right? I think you just like run around stealing people's cars and mugging old ladies and stuff like that. It's terrible, right? Right?
Awesome.
So
The only game I enjoy playing.
wouldn't it be awesome if you could carjack the magic school bus?
Yes.
Like you just kind of check Miss Frizzle out and take it, lock the door.
Talk about take McFrizzle.
Right. Hostage. Take the Frizz hostage. Okay. Well, the thing is, you steal the magic school bus, and where are you going to drive it to? The sun. Because they always go someplace cool, right? We're going to drive it to the sun. It turns out, and a lot of you may not know this about the sun, in the center of the sun, there's this control room. It's air conditioned. It's not so bad. Okay. Right in the middle of the sun. And they have this big dial there. It says gravity. Gravity stronger, gravity weaker. If I went down there and I said gravity, you know what's scary? The look on your face is you're like, seriously? Right. So if I took that dial and I went to gravity weaker, would it change the order in which the planets orbited the sun? Who'd be the closest?
Green.
Who'd be the furthest of these four I wrote, the four rocky planets?
Venus?
Mercury, Venus, Earth, and Mars. Who'd be the farthest?
Mars.
They'd still be in the same order, right? But how would their orbits change, do you think, if the sun was suddenly weaker? What do you think, Ian?
They would go in closer to. No, they would go farther out.
Well, make up your mind. It got weaker. What's going to happen?
They would go farther out from the sun.
They would drift a little bit away, wouldn't they? They still orbit, they just drift farther away. I take that down, I turn up the gravity. Crank up the gravity. Now what happens to them?
Crank up the heat.
Closer.
They orbit, but they orbit. Go ahead, what do you think, Britt?
Closer.
They're going to get pulled in closer. Look at this. I have now, instead of it being gravity pulling on planets, it's protons pulling on electrons. I still have these four orbits, if you want to think of it that way. But I'm going to go from a pull of 19 to a pull of 36. So basically what we're doing is we're almost doubling the strength of the nucleus. It's pulling in harder. Yes, I have four energy levels. I have four layers. However, those four layers are pulled in tighter by the more powerful nucleus. 1, 2, 3, and 4. Does this make sense?
Yes.
That because the nucleus is stronger, it's going to pull in on the electrons, making the atom, this hurts my knees, smaller. Okay, now, note to self, don't do that next time, okay? Making them smaller. Which atom do you think is smaller? Element 20, calcium, or element 30, zinc? Which one is going to be smaller? Lily Campbell.
20. Calcium.
Is going to be smaller than zinc? Calcium or zinc? Who's got a stronger nucleus? How many protons in a calcium nucleus? Test is coming up, Lily, now. How many protons in the nucleus of calcium?
20.
And how about in zinc?
30.
So zinc is like basically 50% stronger. So what's that going to do to the pull on those electrons?
Oh. Make it close.
It's going to pull them in. So as you go this way, it gets smaller. So what we find is there's a trend. As you go this way, the atoms tend to get because what makes them bigger?
Large.
You're adding rings. You're adding energy levels. As you go this way, do they get bigger or smaller? Why do they get smaller? What am I adding? I'm adding protons to the nucleus, making a stronger pull. So let's just go on a hunt for, let's make it the biggest atom of all. Yes, Britt.
Wouldn't it francium be? Oh, I thought...
You're stealing my thunder.
I thought you asked.
No, it's a process I want to go. Okay, look, we're going to start right here. Ruthenium. If I want to get bigger, do I go to the east or the west? Go west, young man. As you go this way, I drop from 44 protons down to 37 protons. That lets it swell outwards. It's not pulled as strong. Is rubidium going to be the biggest atom of all?
No.
North or south? Which is going to make the atoms bigger? Add layers. Francium. Can you get bigger than francium?
Yes.
Who would be bigger? Well, actinium actually belongs right over here.
Oh.
And it has two more protons, so it's actually going to pull in a little bit. The answer is what Britt said. Francium is the largest atom on the periodic table. The only one that could be bigger is if we get to element 119, it'd be here. But the thing is, when we make atoms in particle colliders, they don't have electrons anyway. We're really making nuclei, not atoms. Francium is the largest atom on the periodic table. And you know what? That periodic table of yours, you get to bring to the test. If I was you, I would say, man, I'm just going to go ahead and start annotating this periodic table so it helps me even more. I would probably write a little note to myself, put an arrow here that said, biggest atom. That's what I would do. Biggest atom. I might even put, atoms get bigger. More energy. I'd make notes to myself. Yes, sir.
Are we going to have a final answer?
Yes.
Not a final in the sense of a comprehensive test of everything we've learned this semester. you will have a test on our assigned final day, which is Wednesday, but it will only be about the information on the periodic table unit, starting with, atomic number and going through what's coming up this week. Okay? Yes, sir.
Is there going to be a lab on it?
I'll get back to you on that.
Okay.
I haven't looked at the document in a while. Okay, so let's try getting bigger then. Smaller. I want the atoms to get smaller. All right, Paige, if I want to get smaller, which direction do you suggest I go from Francine? You want me to go this way? Is 118 the smallest possible one? I agree. As I go this way, they're going to get smaller because I got more protons.
Oh, then do you need to go up?
I can go up.
Oh, wait. Okay. Never mind.
What? Go up or not go up?
Go up.
Go up? Go more or less what?
More.
Becca?
Go all the way up to helium and then go left again to hydrogen.
Well, if I go up to helium and go left, I'm going from 2 protons over to 1 proton. So it's a weaker nucleus, and when the nucleus is weak, the electrons swell outwards. Who's the smallest atom on the periodic table? Helium. I'd make a little note to myself. Smallest atom. In this corner, weighing in at 4.0026, is that 260? 260 atomic mass units. He's small, but he's tough. His name is helium. And in this corner, the biggest atom of them all, francium, weighing in at 223.0197 atomic mass units. These two corners, the francium corner and the helium corner, are really important on the periodic table because many trends on the periodic table vary in a fairly predictable way as you move from here to here. Let's start with size. Is this a big atom or a little atom?
Little.
So what we find is the closer I get to this small corner, the smaller the atom. And the closer I get to the big corner, the bigger the atom. So tell me, which atom is going to be bigger? Zirconium, which is element 40, or cesium, element 55? Element 40 or element 55? Asia. Element 40, which is here, or element 55, who's bigger? Yes. This corner is bigger. Cesium is going to be a bigger atom than zirconium. And on the back side of your fancy periodic table, we can look that up and verify that. Let's see. Cesium has an atomic radius of 265, and zirconium is 161. It definitely worked. Now, it doesn't always work, but there's this general trend. I want you to tell me which atom do you think is going to be smaller? Who's going to be smaller? Aluminum or zirconium? Aluminum or zirconium? Aluminum is element 13, zirconium is element 40. Aluminum, zirconium. I want to know who's smaller, and the person who's going to tell me is Victoria. I quite agree with you because we're getting closer to the small corner. Now, and who's the smallest of them all? Helium. And to try to prove that to you, here's what I'm going to do. First period, I inflated this orange balloon with, as a matter of fact, I don't even know how to do that anymore. I had to weigh it down a lot because it was so buoyant, with helium. Okay? And I took another balloon, and of the same brand, in fact, and I inflated it with air. And we were very careful to make sure they were the same size.
Mm-hmm.
They aren't the same size anymore. Which one got smaller? Oops, helium got smaller. Who thinks they can tell me why helium got smaller? Go ahead, sir.
It can escape a lot easier.
From what?
The balloon.
Yeah, this balloon looks like a solid wall of fabric, but actually, just like the fabric of my shirt, there's little tiny holes in it. Now, these are atomic-sized holes, but it turns out air molecules are too large to fit through those atomic-sized holes, so this hasn't changed size at all. But helium is small enough to fit those little atomic-sized holes because it's such a small atom that it escapes or effuses from this balloon. And I bet you by tomorrow this will shrink to about the size of a grapefruit, and this will still be the same size. Now, as this shrinks to a smaller size, the size of the openings between the atoms gets small, and it'll get small to where the helium can't escape anymore. But it's a great example of how small helium atoms are. They are really tiny things. But you know what? If all we were talking about was the size of atoms, what's the point? They're all really small anyway, aren't they? I mean, what could be smaller than atoms? They're so small you can't even see the darn things, okay? But we're not really interested in the size. except that the size informs us about something else that's quite important. And to get you to understand that, I'm going to have to be a little bit creative. But it's just, I like this one, so okay. All right. Takes a little bit of setup. I've noticed something kind of pathetic about audiences who watch movies, and that is we're attracted again and again to sequels. But most sequels are terrible movies. It's a rare sequel indeed that is as good or better than the original. I mean, seriously, I can't think of many at all. Shrek 2? Nah. Toy Story 2. Toy Story 2 is better than Toy Story. But you know, they just keep going and going. And you got like Saw 48. You got what's that?
It's like a scary movie.
Oh yeah, Fast and Furious 22, Scream 85. They just keep going. You know, Iron Man was okay, but Iron Man 6. I mean, come on, give me a break. But the reason they do these bad movies is people will go to them. Once you start a franchise, but people will show up, even if it's terrible, they'll just keep coming. Peter Jackson's going to figure this out. Peter Jackson, if you don't know, is the man, the genius behind the Lord of the Rings movies. All right, one of the geniuses. All right. I think the writers are more genius. But anyway, he's been using Tolkien's source material. He did the 3 Lord of the Rings movies, made $1 zillion, decided to do The Hobbit, the skinniest of Tolkien's books, and made it into 3 more movies. Why? Because it's a sequel that people will go to, right? Once that 3rd Hobbit movie gets made, what has he got left?
Tolkien wrote more books.
Did you have to tell me that? How come nobody's ever read them? They must be bad books.
Probably.
Okay, all right. What if he just says,
Well,
you
you
know
just
what?
said they'll go see
I
it
don't
no
need
matter
Tolkien
what.
to tell me. He says, I've been spending my whole filming career dealing with hobbits and elves and dwarves. I know how to write this stuff. I'm just going to make a sequel like everybody else does, okay? If you can have Saw 7, you can have Lord of the Rings, The Return of the King 2. And we'll just make up a new story with a car chase or something in it, okay? People love that stuff, right? Yes.
Aren't they trying to do Alien?
Oh, yeah. Before they even released the movie, you released the video game. Fine. All right, so my point is, Peter Jackson is going to do the Return of the King 2. He decided he's going to film it in the Olympic Mountains because that looks very Middle-earthy. He's going to build some castles up there. There'll be great tourist attractions. And he needs extras. And so he puts a thing out. I don't know how you do it today. Facebook, I don't know, newspaper. I don't know how you do it. But puts that word, hey, if you want to be an extra in my movie, just show up at room 52 at CK Junior High next Saturday morning. And if you really want to make sure you get a part as an extra in my movie, you need to dress like an elf or a hobbit or a dwarf or something like that. You know what I'm saying? So all these people who are super into Lord of the Rings and go to all the medieval fairs, they make sure they put on their chainmail shirt that they knitted themselves, or their armor plate and their helms of wonder, and they have their two-handed battle axes and all this great stuff. And they show up, and here y'all are, ready to be extras in Return of the King 2.
With the car chase.
And you're waiting for Peter Jackson to come in. But instead of Peter Jackson, who walks in?
Spike.
Me. And I go, hello, ladies and gentlemen. You... What? I'm not Peter Jackson, as you may be aware. I am, in fact, a diabolic madman, and you are all going to die. And he hits a button. And when he hits a button on that wall over there, all these little panels start flipping over, and what was just a wall in a classroom is suddenly covered with landmines.
What?
Why is it
You're like,
on the wall?
that doesn't bother you?
Well, it would run into the wall.
Excellent question. What are you supposed to be? A hobbit? An elf? I can't even tell. An ogre? Okay. Let me push one more button, sir.
Oh.
Who's laughing now? Because when I hit that second button,
explode
I
too?
activate a powerful electromagnet behind that wall. And all y'all thought you were so cool wearing armor, and now it's like, armor's pulling you towards the landmines. Oh! And now you're all desperate to be saved. Help! Save us! Help! Now, Eric Sampson, who's working on superhero status, is walking through the streets of Silverdale, telling litterers to pick up their litter like a good superhero. Hey,
Snapping.
clean up after your dog. Well, I'll beat you up.
Snapping.
I got a cape on and everything, right? And so I just bought a latte at Starbucks to get ready to walk out, and I go, what's that sound out here? Are there people in trouble at CK Junior High? I need to spring to action, so I run into the bathroom there, I change into my yoga pants of glory, and I power walk up to the high school. They need to have a superhero who does this. It'd be awesome. Okay? Yoga pants of justice. That's what I got. Okay. And I go, I'm here to say, whoa, are those Claymore landmines on a wall with a powerful electromagnet behind it? You guys are all wearing armor about to die? And you're like, yeah, I'm out of here. And I go, oh man, I'll totally lose all credibility as a superhero. Okay, I'm going to save one of y'all. I'm going to save one person here so I can be interviewed in the newspaper and build my stature as a superhero. Could save Marissa. She's the one, she's right next to them. She's the one who's crying out the most for help. Help, help, help. Well, here's the thing.
She'll explode first.
She's right next to the magnets where the force of the magnet is very strong. The force of a magnet is inversely proportional to distance. In other words, every time you get 2 times closer, it gets 4 times stronger. And girl, you are right next to that magnet. It would be really hard to save her. I mean, I would have to like grab her and just like apply a very strong force across a very large distance. And force times distance equals work. And work is energy. It would take a lot of energy to save Marissa, and I might die in the process. So let me think this through a bit. Could come over here and save Ian. Look how far away he is. This far away from that magnet, the force is going to be very weak. So I'll have to apply less force across less distance and do less work. It takes less energy to save Ian, so I save him. Go to the newspaper. Hey, I saved one of them. All right, and now I get to be a famous superhero in yoga pants. Let's turn this around now. Instead of you guys being wannabe elves and dwarves in armor, and instead of that being an electromagnet, you are electrons, and that is the nucleus. Because let's face it, electrons are attracted to the nucleus in a very similar way that people in armor are attracted to an electromagnet. Close to the nucleus. When the electrons are close to the nucleus, it is very difficult to pull them away. I could pull Marissa the electron away, but I had to apply a lot of force across a lot of distance and do a lot of work, which is a form of energy. And so, in doing so, I would take what was an atom, remove an electron from it. It's not an atom anymore. What is it at that point? This is one of the things I'm going to ask you next Wednesday. It's one of the questions on the test. If you remove an electron from an atom, it is...
An isotope.
Starts an ion. It's not isotope. Darn it! Why is it ion? I hate that. Why do they both start with the letter I? It's an ion. So we have a name for this amount of energy that I just expended. The energy I needed to turn an atom into an ion is referred to as ionization energy. And if the electron is very close to the nucleus, it requires a high level of ionization energy to pull it away. Because you're close to the nucleus where the force is very strong. On the other hand, instead of being 1 energy level away, what if I was 1, 2, 3, 4, 5, 6, 7 energy levels away, like francium distance away? Yeah, it works out nice, doesn't it? I'm 7 energy levels away from the nucleus. It requires very little energy to ionize an atom out here when the electron is that far away. Right? So here's what we could do with our periodic table then. The biggest atom has its electron the furthest from the nucleus, making it have the lowest ionization energy. Guess who has the lowest ionization energy of them all?
Francium.
Say it like you mean it.
Francium.
Francium it is. You already have an arrow pointing to it that says biggest atom. Why don't we add lowest ionization energy, easiest to take electrons from? Yeah? Seriously? Lowest ionization energy, easiest to steal electrons from. Who do you think has the highest?
Helium.
Hey, not too shabby. As I go this way, the atom gets smaller, so the electron gets closer to the nucleus, making it harder to pull away. Helium has the highest ionization energy, and therefore it is the hardest to take electrons from. Victoria, you got a question?
No.
Okay. Therefore, it is the hardest to take electrons from. Who would be, okay, now, do you guys remember which element I said was the best the most reactive element discovered?
Fluorine.
It was fluorine. It's in this corner over here where the pulling electrons is strong or weak. Which is it over here?
Strong.
This is the strong corner. The electrons are close to the nucleus, they're very strong. Well, here's the thing. Who's got the strongest pull of any atom? Helium. Why isn't helium a good electron stealer? Ian.
Because its rings don't really
It's got a filled energy level. It can steal electron. It's got to know where to put it. Okay? So guess who has the second highest ionization energy, the second highest pull on its electrons of any atom on the periodic table? Neon. Why is neon no good at stealing electrons?
Well, it has all its rings filled.
Its rings are all filled up. There's no place to put a stolen electron. Who has the third highest ionization energy, the third strongest pull? Fluorine. No, it's fluorine. Because remember, the closer you get to here, right? Fluorine, it has a strong pull, and it's got room to put one of them in there. So when fluorine touches something, the reason it catches on fire is it bumps up against something and says, your electron is coming with me. I'm going to pull your electron onto me, and when your electron falls onto me, I'm going to get hot, and that makes things start to glow, and we call it fire. So basically, everything fluorine touches, it's able to pull electrons away from because it's stronger than everybody else when it comes to pulling electrons. Now, another great electron stealer is one that's more familiar to us. Who do you think would be another really great electron stealer?
Oxygen.
Oxygen is a great electron stealer. I got a bunch of oxygen here, and I have a bunch of oxygen in here. Which one do you think contains more oxygen? The big beaker or the little beaker?
Little beaker.
There's a lot more oxygen here. It just happens to be part of water, which is
H2O.
H2O. I want to talk a little about H2O, why it's H2O, and just keep in mind that oxygen likes to steal electrons. So here's oxygen. It's oxygen has, let's see, how many protons does oxygen have? Take a look at it for me, Nicole. Are you looking at the periodic table? Oxygen.
How many like?
How many protons?
8.
8. Okay, so it's got 8 protons. It's going to attract 8 electrons. How many fit in the first energy level? Come on, people. 2. Leaving me how many more I got to park?
6.
How many can that second energy level hold?
8.
So 1, 2, 3, 4, 5, 6, 7, 8. I got room for 2 more. And what happens is this. Oxygen is great at stealing electrons. It's the only person who's better, the only atom who's better is fluorine. And it comes across an atom of hydrogen, which has a whopping 1 proton orbited by 1 electron. Let's see, I'll do this one in black. And oxygen says, give me your electron. And that's a terrible, look for that nucleus ended up. Right.
It's a beautiful circle, though.
And then here's another one. And it's got 1 proton here. And it's got this electron here. And oxygen says, give me that electron. That's why it's H2O. Right? Now the thing is, look at hydrogen on the periodic table. Way up at the top. When you get way up to the top of the periodic table, does that make you have a strong pull or a weak pull on your electrons? Are the atoms getting bigger or smaller? As the atoms get smaller, the electrons get closer to the nucleus. Does that make you have a stronger or weaker pull? Turns out hydrogen is not exactly easy to steal electrons from. So think of it this way. Think of oxygen like a purse snatcher, like a New York City purse snatcher, okay? I want to steal some lady's purse today. It sees this lady named hydrogen. The electron is her purse. Give me that! Except, unfortunately for oxygen, this isn't just any old lady. This is one of those bodybuilder ladies who pumps a lot of iron. Give me your purse, lady. No. He's got it. Give me yours. No. So he's trying to pull these purses away, and they're not letting go. That's what's going on here. We're going to learn to call it a covalent bond, but right now, oxygen can't pull hydrogens. Nobody can pull hydrogens electrons away. So here's oxygen struggling, right? What if some lady comes along who isn't a ripped, steroid popping weightlifter, and she goes, "What is going on here?" And her purse is like dangling from her delicately painted fingernails. Oxygen's like, why am I holding on to these purses from these ripped muscle ladies when that one's just dying to be taken? So I'm going to take her purse instead. In order to do that, what do I have to do with this purse? Let go of it and grab that purse, and let go of it and grab that one. If I let go of hydrogen, where does it go?
Away.
Narnia.
Green means it's a gas. If a gas starts forming here, where's it going to go?
Bubbles.
In the form of
Okay.
bubbles, air, bubbles. All right, so let's just see if that happens. Let's see if there's an atom that's got a weak enough hold on it that oxygen's willing to throw away its hydrogen and grab the electrons away from it. Let's start here with magnesium. Here is a piece of magnesium. Magnesium. I'll know it's working if I stick it in here and I see bubbles. Do you see bubbles? Do you see bubbles? Is it working? Can you see it? Do you see bubbles? No, you don't see bubbles because you know what? Magnesium has a pretty good hold on its electrons. It's like, I ain't going to let go of my electrons that easy. It's like, it's not worth pushing away that one to grab those. Now, I have two other elements we can choose from. Beryllium or calcium. Think before you talk. Of those two, beryllium or calcium, which one's bigger? Does that make the electrons closer to or further from the nucleus?
Further.
All right. Who would be easier to take electrons from, beryllium or calcium?
Calcium.
So if I put beryllium in here, would it make bubbles? Magnesium doesn't. Would beryllium? No. Calcium? Maybe. Let's just see. Here's a piece of calcium.
That's a piece of calcium.
I happen to have some calcium in it. That's not a piece of calcium. This is a piece of calcium. Okay, I have a piece of calcium here. I'm going to go ahead and throw it in here. Do you see bubbles?
Yes.
What's in these bubbles?
Hydrogen.
These are bubbles. It's not air. It
Hydrogen.
ain't water.
Hydrogen.
It ain't calcium.
Hydrogen.
That is the oxygen letting go of hydrogen, and so the hydrogen turns into bubbles and drifts upwards. The calcium is having its electrons snatched away from it by the oxygen, and the oxygen has to let go of the hydrogen to do that. Okay? I love hydrogen. Do you know why I love hydrogen?
It's flammable.
That's why I love it. It's flammable. Now, I have an adage. If some is good, more is better. Abby, I need to get ready with the lights. What's that?
How far back should I be?
Oh, this is great. Let's see. Don't turn off. Don't turn off quite yet. Can you see that? Zoom on in on it there, Britt. You got it?
Mm-hmm.
Hey, I think I'm making some hydrogen here. Why don't we turn off the lights? All of them. The Eric Sampson and the beaker of fire. That's hydrogen gas that's being liberated. And, Bryce, where is that hydrogen coming from? The bubbles, because the oxygen is letting go of its hydrogen in order to grab the electrons that belong to the calcium. Now, notice that beautiful orange color?
What's it make?
That's because there's some calcium ions floating around in there.
Mr. Sampson,
Yeah?
what's it make once it the hydrogen combines with the calcium?
Oh, what's that again?
What does the hydrogen and calcium make when they go together?
Oh, no, the oxygen is combining, the oxygen is
yeah.
grabbing the calcium. The hydrogen is being released. Then when I do this, the
Oxygen.
hydrogen is reacting with oxygen.
Well, what does the oxygen and the calcium make when they go together?
It makes calcium oxide.
Oh.
Or calcium hydroxide. I could have looked this here. Lights on, please. Ooh, wow. This water is super hot.
You have to let it cool.
It is really, really hot. It's so hot I can barely touch it. And that's because when electrons fall off the calcium onto the oxygen, they let go of some energy, and it makes it really, really hot. So we find that chemical reactions tend to release heat, and sometimes the heat alone is sufficient to react its own hydrogen. Now, not in the case of calcium. Now, ooh, that is so hot. Let's see. I need to find something I can grab with. Yes, ma'am.
Would something extremely severe happen if you were to put your finger in there?
Are you trying to dare me or something? No, except I get burned because it's very hot. I mean, this is really hot. Feel it. Touch this to see how hot it is. It's so hot.
It looks like
Touch it. Man, it's so hot. You want to stick your finger in it? No, me either.
He's just cleaning out the cup.
Ow. It hurts. All right, let's try this. When I went from magnesium to calcium, what happened to the strength of the pull on the electron? Did it get stronger or weaker?
Weaker.
It got weaker, and oxygen pulled it away. Here it didn't. I'm going to go from magnesium over to aluminum. Is this pull going to get stronger or weaker? It's going to get stronger, and therefore I'm not going to be able to pull these electrons away. Aluminum doesn't make bubbles when you put it in water.
What about
What if I went the other way? Stronger or weaker? And weaker means easier to steal from. So now, I would imagine sodium is probably likely to react with. Let's just try this. I got lithium, sodium, and potassium. These three elements here. Of these three, which one do you think is going to be the most likely to react with water?
Potassium.
Which is the least likely?
Lithium.
Because as I go this way, the atom is getting smaller, the electrons are more tightly held. So Britton, if you bring that camera over this way, we'll try this. We're going to make, and if you're on that side, you may want to walk over this way, but you don't want to get too close.
You gotta use your desk. Sorry.
Samson, you gotta get a steady cam.
I do what?
You gotta get a steady cam.
A steady? Can that be awesome?
So like,
Or a GoPro. Oh. I can just wear a GoPro on my
you know what
head.
steady cam is?
That's what it said. They use inertia so it doesn't bounce around.
Yeah, but it's like $800.
Oh, they actually sell them? Here's lithium.
How'd you say? Pricing off price this.
Now, lithium is a metal that's so soft you can cut it with scissors. In fact, all of these alkali metals are. So I'm going to cut off a piece of lithium here.
What is it? Oh,
Is that
doesn't it
poisonous?
like
Now look where I cut it. Where I cut it, it's very silvery.
it reacts with oxygen?
It's a mineral water.
I put in this mineral oil to keep it away from oxygen and to keep it away from any water that might get in there. Now I'm going to put some sodium here. Again, the sodium is kept in this mineral oil to keep it away from water and oxygen.
Okay, that's sodium.
Here's sodium. Here's a piece of sodium. So let's do this. Take a piece of sodium. It's even easier to cut with scissors. And then let's get some potassium. They won't sell me very big things of potassium anymore.
Why is it?
Too many people got hurt. So they said no more big potassiums.
You have yellow
Yeah.
phosphorus?
The first time I got my hands on some, I was like, whoa, what happened there? It was a little bit more energetic than I anticipated.
Oh, bananas
Let's put
are
it-
dangerous.
Did someone get their hair on fire?
No, it wasn't quite that bad. But it was more energetic than anticipated. All right, so I've got lithium, sodium, potassium. Of these three, which one do we anticipate to be the least reactive?
Lithium.
Lithium, okay? Smaller atom, electron closer to nucleus. Which do we anticipate to be the most reactive? Potassium. potassium, biggest atom, electron furthest from the nucleus. Let's try. We'll put. Is lithium reacting?
Yes.
It is. And you know, it's going to take it a long time to react. It's just going to react and react and react and react. So I'm just going to let it keep reacting. You know what I'm going to do now? I'm going to go ahead and put this on the sodium. And sodium reacts so much it will catch itself on fire. I didn't get it all. Okay. Potassium, now the lithium's still working at it. Still not all the way gone and still hasn't caught on fire. Potassium goes instantly. Okay? So it's just like you thought it would be. That as you go further down the periodic table, those electrons get further from the nucleus, they get easier to steal. Now tomorrow we're going to take the sodium and have a little more fun with it.
Bye.